So now we're in a position where we can talk about a phenomenon called adsorption. Notice the spelling of this word carefully. It's adsorption with a D, not absorption with a B. Absorption, a more common word in everyday English. If something is absorbent, it means it absorbs something, which means the thing that it absorbs is drawn within or inside it. Adsorption, the AD prefix, means that something is attached onto the surface of it rather than drawn within it. So we're talking about adsorption with a D. In general, what adsorption means is some molecule adsorbs or is attached onto the surface of some substrate, which we could also call the adsorbent. The adsorbent is the surface onto which some molecules are attached or adsorbed. The molecules that attach to the surface are called adsorbate molecules. And in general, we're talking about a process that is usually reversible. Molecules can adsorb onto the surface of a material and then later may be able to desorb or detach themselves from the surface. This phenomenon shows up in a lot of different chemical situations. A lot of catalysis takes place via the reactants adsorbing onto a catalyst surface, as in heterogeneous catalysis, or adsorbing onto a protein in the case of enzymatic catalysis or binding to a protein, and then later desorbs after the reaction has taken place. Chromatography takes place by molecules in the mobile phase, adsorbing onto a surface, staying there for some variable amount of time depending on how strong their interactions are with that surface, desorbing and moving further down the mobile phase later on. So that's why molecules get separated in chromatography, as they adsorb to the surface for different lengths of time depending on their character. And most processes involving membranes, like using a membrane for filtration or using a semi-permeable membrane for osmosis, those processes, at least in a practical sense, are more efficient when the membrane remains not clogged up by other materials. So if a membrane gets fouled or gets clogged up by molecules that get adsorbed onto that membrane, then the filtration or the osmosis process is less efficient. So understanding what conditions molecules adsorb onto those membranes can affect the efficiency of those processes. There's two different flavors of adsorption that are sometimes distinguished: physisorption and chemisorption. The prefix phys or chem just indicates whether the interactions with the surface of the adsorbate with the surface are purely physical, like let's say a van der Waals interaction or an electrostatic interaction. If the molecule can adsorb without changing its chemical bonding and then desorb later on, that's a physical interaction. We call that physisorption. So for example, let's say water condensing onto the surface of glass, that's a adsorption process, and we call that physisorption because the water molecule is unchanged. On the other hand, chemisorption, if the chemical structure of the molecule changes when it adsorbs to the surface, then we call that chemisorption. An example of chemisorption would be when water adsorbs onto some metal surfaces like titanium. Then the water actually dissociates to form an H and an OH, both bonded to the metal surface. So we say that water would chemisorb onto a titanium surface. Adsorption can happen in a number of different phases or states of matter. We need some sort of substrate or surface to adsorb onto. In most cases, that's a solid surface, but the thing that adsorbs onto the surface might be a gas molecule, might be a solute molecule. So if we have a solution in contact with the surface, if solute molecules precipitate out of the solution onto the solid surface, that precipitation process, if they precipitate onto the solid, is called adsorption. But also, gas molecules can adsorb onto a solid without the presence of a solution phase. And sometimes the solution, the substrate that molecules adsorb onto can remain in the solution phase. So if we have, let's say, protein molecules dissolved in solution and the protein is the substrate molecule, smaller ligand molecules can adsorb onto the protein molecules, and that would still be an adsorption process. Next, we can consider the thermodynamics of how adsorption proceeds, and this is going to be what makes adsorption an interesting process to think about chemically. Let's say we have a case where a gas molecule is adsorbing onto some surface, so it's changing phase from the gaseous state to the adsorbed state. In general, the energy or the enthalpy of that reaction is going to be negative, meaning that in the gas phase, the molecule is not interacting with any other molecules, but on the surface, it's interacting usually favorably with the substrate surface. So the energy has gone down when the molecule adsorbs to the surface. So the enthalpy change for adsorption is going to be a negative number. The entropy, if we think about what happens to the entropy, in the gas phase, the molecule has a lot of different configurations that it can occupy. It can be in any position within the box. When it's adsorbed to the surface, its conformational freedom is very much restricted. It's adsorbed to a particular location on the surface. Its internal geometry may be restricted to a particular geometry when it's adsorbed to the surface. So the molecule has gotten much more ordered when it adsorbs onto the surface, so its entropy has decreased. So in general, certainly true that the entropy decreases when a molecule adsorbs to the surface. In most interesting cases, the energy or enthalpy also goes down when it adsorbs to the surface. What that means is that the free energy, if the enthalpy is negative for adsorption, if the entropy is also negative for adsorption, negative number minus this negative number might be a positive result or might be a negative result. So depending on the temperature, depending on the balance between the enthalpy and the entropy, the free energy of this process could be positive, so it could be unfavorable, or it could be negative, or favorable and spontaneous. So in many cases, the free energy is near zero, which means that we have an equilibrium process. Gas molecules or solution phase molecules will reversibly adsorb onto the surface and desorb in some sort of equilibrium. And we'd also expect that we can see changes in the strength of that equilibrium depending on the temperature. So if we increase the temperature and favor the entropy side of this expression more often, then at high temperatures we expect the molecule will tend to desorb because entropy will push it back into the gas or solution phase. But if we lower the temperature so the entropy term is less important, then it'll be driven by the enthalpy, and that will drive molecules onto the surface. So we expect we should see pretty strong differences in behavior as the temperature changes. So the next step is going to be using the tools we've developed in PCAM to come up with some quantitative models to try to understand exactly how it is that temperature and pressure and other thermodynamic variables affect the adsorption process.